Sorry, CEA. Here we go. Um, we had our last video, we ended by checking to make sure that our beam would hold the shear that was required of it. We also figured out what our shear was. Basically, our shear is our where is it at here? Our shear is our end reactions, which are these 9,000 pounds on RYA and 9,000 pounds on RYB is our shear load. And then we multiplied that by 1.5. So basically our safety factor and got 13,500 pounds of shear on each end. So we had to check to make sure that our beam would hold that, and our beam holds 71,460 pounds of shear, so plenty. So that's why we marked it good. And the beam we had chosen was a wide flange 12 times 14. Okay. We also had figured out our max moment, which is right here. And then we multiplied that max moment of 40,500 pounds by a safety factor and came up with 67,635 pounds of moment is what our beam had to hold. And then we went on in and used that safety factor moment and figured out what our plastic modulus was. So in choosing a beam that has a plastic modulus of at least 16.2, we know that our beam is going to be strong enough to hold our moment. So we've already checked our moment, and this is us checking our shear. The last step then is to check our deflection. And then, so in order to do that, we have to do our deflection limits. So deflection is length divided by a number. Usually it's either going to be L240, well, it's going to be L120, it goes up by 120, L360, L480, L600, L720, and so on. And so a deflection limit down here is going to allow the whatever building member it is, whether it's wood or steel, to bend more with a load on it. The further this way you go, the less it's going to be allowed to bend. So let me show you our limits. Okay, we are going to choose an L240 for our dead load plus our live load. Okay, so the length, here's the kicker, the length has to be in inches. So it's going to be 18 feet is our length over 240. We got to convert that to inches. So 18 times 12, I think it's 216 divided by 240 will be our deflection limit for our live load plus our dead load. So if we say 200, well, let me just double check that. 18 times 12 is 216 divided by 240. Okay, 0.9. So our deflection limit is 0.9 inches. Okay? So basically what that means is our beam cannot flex more than 0.9 inches with the load that we designed for it to have on it. And the reason for that is you connect things to those floors like drywall or plaster or mechanicals like water pipes. And sometimes those can't move very much or it damages them. So you really have to make sure that you don't allow your floors to flex with the design load on them. Now you put way more than your design load on them, they might flex more than this. So you have to make sure you design your floors to hold plenty of weight. That's part of why we put our safety factors in there. Anyway, so that's our limit. So now we have to actually figure actual deflection. And this is done with a simple formula, actually. It's a little bit intimidating, but the formula is pretty straightforward. It is this formula right here. So I'm going to go ahead and write that down. So we have because our live load and dead load are uniform loads, this is how we figure out our deflection. So 5W to the fourth divided by 384 times E times I. Okay? So we say 5WL to the fourth 384 EI. So now our I we got, I'm going to go ahead and shrink this and I'm going to go here. We got our I because we chose, this is our beam right here that we chose. And your I is literally this column right here. It's going to be this number. It comes right off the chart. So 88.6. Our Z is here. This is how we choose our beam, right? We had our plastic modulus of at least 16.2, and this was the closest to 16.2, but over. And then we have our 88.6. So this is our I. They also gave us, hold on here. I'm going to go back to my camera. And they also gave us, on the first part of our assignment, our E for structural steel. That is, it's a structural factor in your steel. So it's 229 million. So we now have those numbers. Okay, so let's do this. If we rewrite this, it's 5 times our W is our load, that was 1,000, times our L, and that is 18 to the 4th. Now, and then we go 384 times 29 million times our 88.6. Here's the thing, and I don't want to spend a lot of time on this. I am already at 6 minutes on my video, so because you have all kinds of different units, so like this is PSI, pounds per square inch, and this is, I think, inches to the 4th, and this is 18 feet. So anyway, I'm going to go ahead and write this the way they did. It's 5 times 1,000 over 1. So this is 1,000 pounds. And then this is times 12 over 1. I'm sorry, I did that wrong. It's 1 over 12. I just double checked. It's 1 over 12 times our 18, that's feet, times 12 over, that's 18 over 1. This is 12 inches over 1 foot to the 4th. So all of this, I don't want to go through this all right now. We could write this out. And what this does, the reason they write this out is because you start canceling out units, right? I cancel out feet, and you guys should know from algebra that anytime you have like inches on the top and the bottom of a denominator, you can cross them out and they disappear and you're left with other units. So they do this throughout this formula. Just trust that, because so essentially 1,000 over 1 times 1 over 12 is 1,000 divided by 12, right? And 18 times 12 is going to be more than, it's going to be 216. And then you take 216 to the 4th power. So you have to put these into these forms. So basically you're dividing your W by 12 and you're multiplying your feet by 12 before you do this formula to cancel out units. Just understand you have to modify this in order to cancel out all the units. Okay, so I'm going to go ahead and write this. 384 times 29 million times 88.6. Now, I'm going to give you a lesson in class on how to type this into the calculator. You have to use PEMDAS and all the parentheses first, exponents second, multiplication third, and so forth. I don't want to go through that, but I will show you how to type this into a calculator during class. Don't want to use my video time. This will come out to 0.9, and the units you have left over are inches. So after you cancel all these out, because I divide by 12 and because I multiply by 12, you're going to be in inches. So this is how much that beam can, I'm sorry, this is going to be 0.92. I apologize, 0.92 inches. Okay, so that is our actual deflection. This is what we were allowed to deflect. Since that is more than that, we have a problem. So you got to say no good. Too much deflection. So what we're going to do is we're going to say move to 12 by 16. W 12 by 16. Okay, and then we're going to write some numbers over here. So I'm going to click out of this. We're going to go back to our chart. And here we go. Here's our 12 by 16 right here. 103 and 20.1. So our z is 20.1 and our I is 103. Okay? I think that's what we need. Okay, so I'm going to come back down here, put this back on, and we are going to do this again. Okay? Well, actually, we're not going to do this again because they give you, once you do this, if you have to choose a new beam like we got here, just write down these two numbers, your Z and your I, and then they give you a little formula. So they say 0.92, which is what our deflection was, times our old I divided by our new I is going to equal what? This will be your new deflection. So 0.92, oops, 0.92 times, and then we're going to put in this is in parentheses, right? 88.6 divided by 103, close parentheses, equals. We get 79.137, so 0.79 inches. So our new deflection is 0.79 inches. So we are good. Okay? So that is our dead load and live load together. Last thing here, they give you a live load, and they want that to be, it's the same formula, right? So it's 5WL to the fourth over 384 EI. So our live load equals L over 360, and our live load is 667 pounds. Up here it was 1,000, right? Up in here it was 1,000, so this is going to be 667. So, but for our length here, our length is still going to be 216 divided by 360. We're going to be able to not bend as much. So if I go 216 divided by 360, I get 0.6. So that is now my new limit for just my live load. We got to make sure we meet the dead load plus the live load at L240, and we got to make sure we meet the live load at L360. So we're going to write this in there, 5 times. This is going to be 667 divided by 12 times 18 times 12 to the fourth divided by 384, 229 million, and we wrote our I right here, right? 103 times 103. Okay, so I'm going to go ahead and type this in, see if I can do this, and hopefully we're good. So, parentheses, 5 times, parentheses, 667 divided by 12, close parentheses, times, open, 18 times 12, closed, to the fourth, oops, closed, divided by, open parentheses, 384 times 29, 123, times 103. And so when I do all that, I get 0.527 inches. Okay, since 5.527 is less than 0.6, we are good. Okay, so up here I probably should have done the same thing. 0.79 is less than 0.9. Good. So we have met our deflection limits. We are going to have, this is our beam right here. We're going to have a 12 by 16 wide flange I-beam. Okay, now that is how you do this. And now we have to do this. This is just our interior beam. Now you got to figure out all of this for your next beams as well. All right.